Swayam Prabha. Digital India. Educated India.
A little bit of a history for about 40 minutes. This is a very beautiful story. Professor Chandrakumar is our own former faculty member of the chemistry department. Very well known international expert in the nuclear magnetic resonance spectroscopy. He is 70 plus now. He retired last year, 2 years ago, and he comes to the office once in a while. If he is free, I would request him to give you a couple of lectures towards the end of this month. Okay? He is an expert in the whole field of magnetic resonance, quantum mechanics, statistical mechanics, and in general, both the experiments and theory of magnetic resonance imaging. He's very, very famous for, well known for that. And at my request, about 3-4 years ago, he gave a lecture on the COVID time during online lecturing. It was one of the seminars that he gave, and the topic is about the discovery of spin. The spin was first observed experimentally by two people, Otto Stern and Gerlach, two physicists. It's a very nice anecdotal story. I will be here for 40-45 minutes, or I don't know exact time that it's running on. And my lecture will follow from that basic component that he talks about. I've listened to it several times, but I will continue to listen to you. Okay, initially,
now let me start the seminar without further ado. The story starts almost 100 years to this day,
everybody,
about 1920. And there was this notion floating around from Bohr and Sommerfeld and others, which they call the space quantization. What they meant by this was that because of the restriction and the possible values of the z component of angular momentum, where z is an externally defined but otherwise arbitrary direction, along which you might choose to impose, for example, a magnetic field, or if it's a Stark effect.
What he is going to describe is magnetization is quantized in space. Quantized means it has very specific directions. It's not magnetization in a classical sense can go from North Pole to South Pole in any direction given enough energy. It can orient itself. You can push the magnet with a little more energy, it can point in the different directions. All orientations, basically it's the infinity of orientations. If you talk about this direction to this direction continuously, it's infinite orientations. That does not happen for nuclear magnets and electron magnets, electron spin. And this particular magnetic property was proposed by theoreticians, theoretical physicists, that it could also be quantized in space, but there were no experiments done. And he talked about Niels Bohr and Sommerfeld as two scientists who predicted that magnetization can be quantized. But they also did not do the experiments. They are both theoreticians. They were both theoreticians. And Bohr, of course, did fantastic experiments with Rutherford at that time. But later, two scientists came and started doing this. It's a very nice anecdotal story.
An electric field, some reference direction called Z. So they found that there is a restriction on the possible values of the Z component of angular momentum. And this, of course, automatically means that the angular momentum vector can have only certain orientations in space. And this was termed as space quantization. Now, the strange thing about this, dear audience, is that the very theory people who had forwarded this proposal and made this name or this nomenclature actually did not believe that this was any physical reality.
Yeah, the theoreticians who first proposed this did not think that that would be true, it would be real, but they still proposed it. They didn't have any experimental evidence, but they believed, but they were not sure that this would ever be experimentally noticed. Please remember, quantization of magnetization is so important in every field of chemistry, physics, biology, wherever magnetism is involved. Magnetism is a quantum mechanical property of the nuclei, and the bulk magnetization that you experimentally measure and you use is all the collective behavior of all the tiny billions and billions of magnets together.
It's just something in our thought, in our mind. There's something we call the space quantization, because the Z component of angular momentum can have only discrete values, and therefore the angular momentum vector can have only certain discrete orientations in space. But this is not a physical effect. But then they did not reckon with Otto Stern. Now, Otto Stern, for chemists, you will remember, is also named, the Stern-Volmer equation. This is the same Stern that is the villain of the current piece of Discovery of Spin. Okay, the villain or the hero of the piece, as you may wish to call him, one way or the other. This is the same Stern who did the Stern-Volmer equation as well. Okay, now this guy, I've heard some ads in the past several years when there used to be a popular TV brand which was supposed to be the neighbor's envy and the owner's joy or owner's pride. Now,
what does that mean? The TV advertisement? The neighbors are envy, the owners enjoy. What does that mean? You have the TV, you listen to the advertisement, put it in big volume, but it's nuisance to the neighbor who hears that all the time. So the neighbors also, you have a beautiful TV, the neighbor doesn't have. So this is the old idea. The neighbors envy, the owners enjoy.
But then they did not reckon with Otto Stern. Now, Otto Stern, for chemists, you will remember, is also named, the Stern-Volmer equation. This is the same Stern that is the villain of the current piece of Discovery of Spin. Okay, the villain or the hero of the piece, as you may wish to call him, one way or the other. This is the same Stern who did the Stern-Volmer equation as well. Okay, now this guy, I've heard some ads in the past several years when there used to be a popular TV brand which was supposed to be the neighbor's envy and the owner's joy or owner's pride. Now, Otto Stern was probably the theoretician's nightmare, but then equally or even more so, he was the experimentalist's nightmare as well, as we shall see. So Otto Stern said, okay, if there is space quantization, let me try to prove it. Of course, he was a skeptic. He said, okay, let me set about the task of proving it. And later on, this is what John C. Slater had to say in his book in volume 1 of the Quantum Theory of Atomic Structure, that Stern and Gerlach in the early 20s, between 1920 and 22, wished to demonstrate the space quantization of atoms experimentally. They produced a beam of atoms of silver vapor by evaporating them from an oven at about 1,000 degrees Celsius and suitably collimating the beam of relatively slow atoms. They then passed these atoms through a transverse magnetic field. What you mean by transverse is that the direction of propagation of the beam and the magnetic field were perpendicular to each other. That's what we imply by a transverse magnetic field here. It is transverse to the motion of the beam of atoms, which would then be expected to space quantize the angular momenta, also transverse to the direction of motion, and then pass it through a transverse inhomogeneous magnetic field in the same direction, in the same perpendicular direction.
So what they did was collimate the beam. It's called a collimator. This is the oven, silver atoms. The beam is collimated with a transverse magnetic field. Yes. So the field direction is perpendicular to the direction of motion. Yeah. What is it called? Collimated means, if you pass something through the nozzle, slowly things start expanding, like the light cone. Laser is more like a collimated light cone. Coherent wave, therefore they don't decohere. It's a collimated beam essentially means that it does not diverge and all species pass through in a very narrow bore uniformly. So to do that, you can do it by passing it through a tube. The beams will not. But still the beams will hit the sides of the tube and there may be scatter. So to the extent possible, you want the flow to be very straight. So this process is called collimating. Okay? So then they pass it through an inhomogeneous magnetic field. Inhomogeneous magnetic field, north-south, what it means is that the field at this point, everywhere, the field will be different. So there is a gradient field. See, if you have different heights, then there is a potential. The gradient of the potential gives you the force. Something like that. The gradient field will be there, so it is called dou H by, if you call this as the z-axis, the field at various points will be different, so it is dou H by dou Z. This acts as a force and rotates the magnetic moment, deflects the magnetic moment, just like the magnetic moment. Suppose silver atoms and other things have magnetic moment. So the whole idea is to say that the magnetic moment of silver atom is quantized in specific direction with respect to an external magnetic field. So what it says is that suppose the silver atom gets deflected due to that, different magnetic moments. What you would see is that on a screen, you would see everywhere. If it is space quantized, what will happen? That's the lecture.
Not the third.
H is the magnetic field. Okay? This is the Z direction. Okay? The field direction is called the Z direction. Therefore, with respect to the Z direction, the magnetization is not everywhere, but it is quantized. Yeah. Yeah, this is a partial differential equation because the magnetic field is with respect to one directional quantity, and also there are other magnetic forces. So what you want to do is to control the derivative of this, the change. You only want to look at the gradient in one direction. The gradient can be in all three directions. Therefore, what you do is you want to measure the gradient because the magnetic moment, if it is space quantized against this direction, then the gradient in this direction is the one which will affect that. If the space magnetization is quantized in this direction and if the gradient is like this, the force, what is F dot B? That will be 0. There won't be any effect. Okay? So the gradient is in all directions as you go along. But what you see is that the Z directional gradient is the most important. Okay? To avoid all those things, this is the partial derivative. Partial derivative essentially means fixing one direction, leaving all the other variables unchanged. That's an exact measurement for any change in a specific parameter. Suppose you have three quantities x, y, z, and the function is a function of x, y, z. You want to see what happens only with respect to x. What is the change? When we change x, let's keep y and z constant. Because if you change x, y, and z, all this at the same time, the change that happens may be some combination of all these three. Therefore, if you remember the original definition of a partial derivative, the total change d of any function, suppose a function is a function of x, y, z, df, if you write, it is basically the change of f in one direction keeping y and z constant times the actual change. This is the derivative plus dy plus dou f by dou z dz xy. So the idea is that quantify changes that happen with respect to one variable. The partial derivative is the best example, is the best way of doing mathematically instead of doing the total derivative. But the total derivative is this. Okay? The total derivative is the sum of all the derivatives in each direction multiplied by the actual small changes that happen. That is the dx that you take. So total change will be this. It's like the vector adding. You have a three-dimensional vector. It's a vector in this direction, vector in this direction, vector in this direction. You add all three, you will get that. Something similar to that. So here also you take the partial derivative with respect to only the z, because you want to see what is the quantization of magnetic field with respect to the z-axis. That's right. Okay. Yeah.
Direction is the field itself. The inhomogeneous segment of the field would also be in the same direction. This would then exert a transverse force on each atom. And atoms which have been space quantized in the homogeneous field will now sense forces in opposite directions in the inhomogeneous field. And then they actually found that there are two beams into which the single beam of silver atoms was split. The input was a single beam of silver atoms at about 10 to the minus 5 millibar, coming out from an oven at about 1,000 degrees. And there was this magnetic field. The
very low pressure, 10 to the minus 5 millibar. What is atmospheric pressure? 1 point? Small amount. So I mean, it's close to 1 bar, but it's slightly more than that. This is a millibar, so which is 10 to the minus 3 bar. 10 raised to 5 millibar, which means 10 raised to minus 8 bar. That means the beam is, the number of atoms in the beam is quite small. But please remember, the number of atoms in a 1 mole of silver, is 1 gram atom of silver, is 10 to the 23. So even if you bring down by a magnitude, order of magnitude of 10 raised to 10, you still have 10 raised to 13 atoms in that beam. That is still much bigger than the population of the earth. If you are talking about the human behavior, one human behavior in a sea of the universe in this, what is the population of the humans? About 8 billion. 10 to the 9, 8 into 10 to the 9, 10 to the 10. And here in a small collimated beam, you have 3 orders more than that, 10 to the 13, 10 to the 14 atoms. Therefore, it's possible for you to see collective behavior of the properties of the magnets.
About 3.5 centimeter long with a magnetic field strength of about 0.1 Tesla and a magnetic field gradient of about 10 Tesla per centimeter. So a huge gradient. We'll see towards the end of the seminar that has been exceeded today, but we are talking about 1920 to 22. Okay? And they found that they got 2 beams from a single input beam, they got 2 at the output, which could be detected separately. Now a little bit of the history. So when, Stern tried to do this experiment, he enlisted the support of the experimentalist Walter Gerlach. Gerlach was already interested in beam experiments. Beam experiments had been discovered around 1911 or invented in 1911 by Dunoyer in France. And Gerlach wanted to check the diamagnetic behavior of single bismuth atoms as opposed to a bismuth crystal. And he was therefore fashioning and designing a very highly inhomogeneous magnetic field. And this is where Stern walks in and they decide to join hands. Gerlach has this highly inhomogeneous magnetic field and Stern wants to check what happens to a beam of silver atoms in this highly inhomogeneous magnetic field. Now Max Born was in the same university in Frankfurt when Gerlach was there, and Max Born...
You know who Max Born is, right? By now you must have heard enough of him. What was Max Born's famous contribution? Max Born was the supervisor of Heisenberg, Werner Heisenberg. Okay, Max Born, Heisenberg and Jordan published the first paper in quantum mechanics in 1925 using matrix mechanics. And Max Born realized that Heisenberg was doing all these algebraic tools. Max Born remembered the mathematician David Hilbert. If you don't know the name, David Hilbert and Richard Courant. They were very famous mathematicians in the late last century, the 19th century, 20th century. David Hilbert had introduced this concept of matrices in mathematics, linear algebra. So Max Born was the supervisor of Heisenberg, postdoctoral supervisor of Heisenberg when Heisenberg wrote the paper. And Heisenberg's uncertainty principle, where Heisenberg talked about only the position of the electron and the speed of the electron in an electron gun or a microscope. Max Born realized it's much, much more general than what Heisenberg was doing. There's a fundamental uncertainty between two irreconcilable variables: position, momentum, energy, time, angular momentum components, x component, y component, z component, and many other variables. Therefore, Max Born is the founding father of the matrix formulation of quantum mechanics. And later, he won the Nobel Prize because he gave this interpretation that the absolute square of the wave function relates to probability of measuring the system. That interpretation gave him the Nobel Prize. The wave function was introduced by Schrödinger, who was in the opposition camp. Okay? Schrödinger and Heisenberg, they were in the opposition camps. Schrödinger believed in using wave equations, believed in using modulation, what he called as undulations or waves and so on. Heisenberg believed in keeping objects in an organized form like matrices. They didn't like each other's way of doing things, but then Max Born was in Heisenberg's camp and he interpreted the Schrödinger's wave function correctly, which Schrödinger did not do. Okay? He did not invent the correct interpretation of the wave function. He was very close. And he started disliking quantum mechanics later in his life for all the problems that Einstein, Niels Bohr, and others had. And Schrödinger said, if these are the things, the quantum gems are the things that I ever invented, I'm so sorry I ever did this kind of things. But Schrödinger was a very famous philosopher. And Max Born also came up with the probability interpretation for the wave function. And he was in the University of Göttingen before he left Germany and then settled down in Ireland, in the University of Dublin. And Schrödinger settled down in the University of Dublin. I think Max Born continued. He also moved later to London, if I remember. I'm not quite sure of the history. So quite certain now. I should go back and check. But many of these scientists who would be persecuted by Hitler during the period of the First World War, Second World War, they left Germany, Austria, and German territories occupied by the Nazis at the time. They went to the United States, they went to England, they went to other countries, and so on. And all of them settled in different countries. Okay. So Max Born was a theoretician at the time in the lab, 1920s. So he is not too comfortable with all these ideas. He says, this experiment will not work.
This experiment will not work.
Oh, exactly.
Even the Gerlach experiment, leave alone the Stern part of the story. But then Gerlach quoted a Zurich physicist called Edgar Meyer, who had said in German, kein Versuch ist so dumm, dass man ihn nicht probieren sollte. Translated in English, it says, no experiment is so dumb that it should not be tried. And that is how Gerlach persisted with his notion of a molecular beam, and soon he joined hands with Otto Stern. Now, what shall we say about Otto Stern? As I said, one could view him as the nightmare of theoreticians as well as being the nightmare of experimentalists. He is one of those guys who straddled the worlds of theory and experiments, it looks like. Some people called him an experimenting theorist. Other people said he's not a theorist by training. But be that as it may, this proposal of Otto Stern to look at the perpetuate space quantization of silver atoms.
See, read that fine print, which is the philosophy of science as a whole. The real benefit was to learn how to distinguish which problems of contemporary physics were important and which were not so important, which questions to ask and which experiments to undertake in order to answer the questions. Thus, from a brief scientific collaboration between Stern and Gerlach, evolved a close, lifelong relationship, friendship, which would be the basis for Stern's great achievements. So, I think in science, we learn to ask the right questions, but in the beginning, since we do not know what is the right question, we keep asking the questions. That's why Professor Bala will also tell you every time, don't stop asking the questions. As long as you think that it is something you want to know the answers for, even if everybody else around you seems to know the answer and you don't worry about it. You want to know the answer for yourself. Therefore, you ask. And after some time, you get experience to see, no, this is not the good question. I'll ask the other question. Think about it. And therefore, asking the right questions is very important.
Magnetic field, despite his careful design of the experiment, okay, he and Gerlach took the better part of a year to actually accomplish it. Okay? And once again, Max Born was there to dissuade them. He had said, I tried to persuade Stern, there was no sense, but then he told me that it was worth a try anyway.
That's Max
because
Born.
Please remember, the theoreticians who had coined the term space quantization apparently did not believe in it as a physical reality to begin with. Okay? Anyway, the beam method first employed by Louis Dunoyer in 1911, that's what Stern and Gerlach used. And the actual parameters that the Stern-Gerlach actually, the paper is by Gerlach and Stern, okay, in Zeitschrift für Physik 1921 and 22. And we'll see the references. Actual parameters were 10 to the minus 5 millibar. The length of the inhomogeneous magnetic field was 3.5 centimeters. The magnetic field intensity was about 0.1 Tesla, which is 1,000 Gauss. And the gradient was 10 Tesla per centimeter, which sounds absolutely heroic. And you know, they got a princely splitting of the single incident beam. At the output, it was split into two. And the splitting in the direction of the magnetic field Z was all of 0.22 millimeters. 0.22 millimeters, ladies and gentlemen, which means that if their experimental setup had been misaligned by 0.01 millimeter, that's it. The experiment is all berserk. Okay, so 0.01 millimeter of precision was required in aligning all this, and they saw this, splitting of one beam into two, and the separation of 0.22 millimeter, and space quantization had been experimentally proven.
They got only two beams.
What's happening in the experiment?
They didn't get any
the potential energy of the the magnetic moment of the silver atom in the magnetic field is V is equal to minus mu dot B, and since the field is in the Z direction, you find immediately that the force in the Z direction is the negative of the Z derivative of the potential energy.
The length of the inhomogeneous magnetic field. So what is happening is the magnetic field is very close, the poles are very close, the beam is very narrow. So the entire length of the inhomogeneity period is 0.22 millimeter. You know what is the gradient? 10 Tesla per centimeter. 100,000 Gauss per centimeter. It's a huge magnetic field gradient. Huge magnetic field gradient. And then they had the narrow bore as only 0.22 millimeters. They needed minimum precision was 0.01, so they managed to get about 0.22. So the experiment was extremely accurate for the period of time when no technology was known for producing magnetic fields of such high order. They produced everything using electromagnetic coils in those days. Okay. So now what it says here is the potential, the energy of the magnetic field B interacting with the magnetic moment of the nucleus. Yeah. Go ahead.
Sir, why exactly is that?
Exactly, two beams. That's the whole point. We'll come to that. That is the crux of quantization. If you look at the first chapter on the third volume of Richard Feynman, you are familiar, right? Lectures on physics. Have you Have you heard that? How many of you know this book? Three volumes. Everyone who is a scientist, who wants to be a scientist, should read these 3 volumes. Okay? Whether they want to be a physicist or biologist or a chemist or engineer, it does not matter. This is by Professor Richard Feynman, most famous physicist in the last century, among the most famous after Einstein and Dirac and a couple of others. Richard Feynman was called Dirac the second time, but this time human. Dirac was not considered to be human in the sense he was like Ramanujan. There's no words to describe Dirac, but Richard Feynman had all the beautiful explanations for what all these things was. So Feynman's lectures on physics, 3rd volume, chapter 1, is about Stern-Gerlach experiment, is about a double slit experiment, something similar. That is about the superposition, wave functions and superposition. You must learn why this is important, and of course there is no direct relevance to this particular lecture, but that's a very beautiful lecture to say what is fundamental about quantum mechanics is this experiment, double slit experiment. So he explains everything using that. And what is the next level of discovery was that angular momentum got space quantization. This is, you should know that the mu is the magnetic moment. In the presence of a magnetic field B, the interaction between the two is mu dot B. Okay? And since the B is only in the Z direction, that is the direction of B is called the Z, you will have mu Z and the derivative. Okay? The force will give you mu Z dB by dZ, and that's a force. And therefore you can see that mu Z is connected by this formula, fundamental formula E h bar by 2 mass of the electron. So what it says is that if the deflection happens in all directions, you will see the Z component of the magnetic moment deflected in all directions, and you will see the beams hitting everywhere, okay, on the screen. But no, you don't see anything except two beams. And therefore it looks like magnetization seems to recognize the field and then decides I have to be up or I have to be down. Okay. Until the field is there, until the deflection happens, magnetization doesn't have a direction. The nuclei, all the silver atom, magnets point in all directions. There is no net magnetic moment. The moment you put that in the magnetic field, this aligns the magnetic moments into some directions, and then from this point onwards, this deflects those magnetic moments, and you still get only 2 of them. That's what is called the success of the experiment here, thought to be due to space quantization. Okay, here. A line should appear on the observation screen. That is, magnetization should appear all along the line if there is no quantization. But instead, what was found was that the silver atoms arrived on the screen at only 2 points that corresponded to the magnetic moment plus or minus mu b. Yeah.
So here we consider some arbitrary direction z. So what actually happens with the other 2 directions? Are they continuous or are they also discrete?
No. See, this is another issue. If you do not know the state of the system before you make a measurement, you have no knowledge of the details of that system. The measurement fixes the system into one of the measured values. So here, the process of measurement interferes with the system. It realigns it. See, you cannot, something is going around and you cannot observe it without that realizing that you are observing it. Okay, this is one of the arguments that Niels Bohr gave, that properties which cannot be measured experimentally do not have a priori attribution. You cannot assign them. And in quantum mechanics, the process of measurements, it does not affect, if suppose the beam, all the magnets were in one direction, in the z direction. If you put another measurement unit, nothing will change. The system will continue to be in that same state. But if it is not in one of those states corresponding to experimentally observed quantities, the system will reorient itself and will be fixed in one of them. And here, the fixing happens into one of the two states. So, what is here? We don't know anything about. We'll say all directions are possible. No, there is no net magnetic moment. Okay, before. Sorry, it's before here. All mu is 0. Okay. We don't know. I mean, we assume that there is no net magnetic moment. The moment you collimate this and you pass through this, you see that there are two values, and therefore the mu b is either plus or minus. So nature fixes itself. Supposed to your measurement. Yes.
Sir,
Yeah, go ahead. You don't understand. I don't think I understand too. The only thing is that's what we see experimentally. See, why it should happen is not a question that we don't know the answer to. The question that we can answer is, when it happens, what is the explanation for why it's happening? Okay? We cannot go back and say, what is the origin of quantization? Why should energy levels be quantized? Why is Planck's constant important? When will Planck's constant be irrelevant? Okay, for the energy, H cannot be 0. Planck's constant has a value, fixed value. Now, when will that be irrelevant? It's irrelevant for our dimension. Because if you start calculating, suppose I am traveling at a speed of something like 20 kilometers per hour. Okay, I have a wavelength. Okay, de Broglie tells me what my wavelength is, h by p. And my momentum is the mass of me and my velocity. And if I calculate the h by p, what is my wavelength? Insignificantly small, that I don't distort while I am moving. Okay, I don't look like I am shaping up, shaping down. Whereas if I start moving at a speed much faster and eventually close to the relativistic speed, then you have a problem. Okay, and also if my mass, instead of me, one electron in me starts traveling at a speed, then that electron wavelength at certain conditions can actually be measured as a wavelength. And how do you do that? You pass the wavelength through a crystal, electrons through a crystal, they diffract the electrons. Diffraction is a phenomenon of waves, it's not a phenomenon of particles. Therefore, electron behaves as a wave. Okay? Why do they behave as wave? And why do they behave as particles in the Thomson, in the original Wilson chamber or whatever it is, E by M Thomson experiment? Why do you see a track? The track tells you how the electron has moved. Okay? But on the other hand, the moment you put the electron with a certain speed through a crystal, the crystal spacings are comparable to the wavelengths that the electron would have, and therefore they diffract. So does the electron move as a particle? Does the electron move as a wave? It depends on what experiments you do. Okay? What is the electron? You don't ask the question. In fact, the theory is that electron is made up of 3 quarks. 2 minus 2/3 quarks and 1/3 quark. So that the negative charge of the electron comes from the combination of these 3 quarks. That's a quark model. Right? Then beyond quark, what do we have? We have gluons. And then we have baryons and leptons. These are all particles in that. Okay? So the structure of the system is going deeper and deeper and deeper as we come to know more, and as we can make measurements very precisely. So here the only answer is that nature seems to say angular momentum is fixed in the field direction. If you don't have the field, you can be in any orientation, okay? But then how would you observe? You can't. There is no magnetization, therefore you do not know the individual field direction. The moment you place the magnetic field, it looks like everybody is up or down, okay? And it's not even true. There can be other states which are linear combinations of the up and down states. And that's a qubit state. The general magnet, a 2-bit, a spin a half system, the general wave function for a spin a half system is a linear combination of the up and down states. And that is not a binary system, it's a quantum binary system. And that we start using. Actually, qubits are used and quantum computers are now assembled in small numbers, and you can actually do calculations using them. So it looks like nature offers us a lot of things that we are not very familiar with. And in chemistry, we are very happy, we don't worry about why it is, we make use of it and make money. And that's what you should also do up to some point. Yeah, go ahead.
So, once we columnate the path, right, we are oriented to the z direction. Before we pass it through the inhomogeneous magnetic field, is it possible to calculate the magnetic moment at that point, like in between both there?
Yeah, since it is passing through a magnetic field, there will be some magnetic moment here. But here the beam is collimated, in the sense all the magnetic things are passing through. So between these 2 points, I don't think we can ever measure a magnetic moment. No. Because that will also be in all directions.
Net will be.
That will be 0. The force comes when there is a gradient in this direction, if magnets are pointing this way, if magnets are pointing this way, if magnets are pointing this way. Okay? See, the magnets which are pointing perpendicular to this cannot be seen, cannot be observed, because mu dot B will be 0. Okay? Mu is perpendicular to B, mu dot B is 0. Therefore, any magnet which is in the plane cannot be observed, cannot be deflected, or if it's deflected, we don't observe them. What is observed is anything which is not in the plane. Everywhere else, the semicircle above, the semicircle below, the ones which are in the semicircle below get deflected in one direction because they point in the opposite direction. The ones which are in the above semicircle point in the opposite, they go in the other way. That's what happens. That's what you will see here in the lecture.
Mu z into delta b by delta z. And when they measured it and found the splitting of 0.22 millimeter, they were able to infer that this corresponded to mu z of either plus the Bohr magneton mu b or minus mu b. That's it. They got exactly the value of the Bohr magneton plus or minus EH cross by 2me. The expectation based on classical physics is that due to the random thermal effects in the oven from which the silver atoms were shot out, the magnetic dipole moment vectors of the atoms should be randomly oriented in space. So there should be a continuous spread in the z component of the magnetic moment of the silver atoms, all the way from minus mu z to plus mu z. A line then should appear on the observation screen along the z direction. Instead, what was found was that the silver atoms just arrived at the screen at 2 spots or 2 points that corresponded to the magnetic moments of plus or minus mu b. So what was the interpretation? The interpretation was this proved the space quantization. The silver atom was then thought to be in the p state with the orbital angular momentum quantum number, which was the only type of angular momentum known up to then, of 1 unit quantum number, split into 2 beams with the z component ml of plus minus 1, and magically it was imagined that somehow the third ml value, the component, the beam with the component ml value of 0 was unobservable. So that's really strange in thinking back now today, right? In hindsight, we are all extremely wise, but this was the interpretation of the Stern-Gerlach experiment. Space quantization was proven, but it was all about the p state of a silver atom, which should have been split into 3 beams, but since the ml is equal to 0 component of the orbital angular momentum would not be observed in the magnetic field, you've got 2 beams, period. And the splitting and the inferred magnetic moment was just right, plus or minus the Bohr magneton. That's what you expect from the ml value of plus or minus 1. So everything seemed to fit perfectly. You expect from the ML value of plus or minus 1. So everything seemed to fit perfectly. Now,
Yeah. So this is all 1921, 22, the experiments were done. And comes the other scientist, Goodsmith, okay? And you can see that, yeah. Goodsmith went through this, and then Paul Ehrenfest was another famous physicist at the time. I don't know how many of you know Ludwig Boltzmann's name. Do you know the name of Boltzmann in your physics class? What is Boltzmann? Maxwell Boltzmann, you have heard. Yeah, Ludwig Boltzmann was probably the greatest scientist ever to have lived after Newton, okay, which many people do not know. Einstein and all, I mean, Einstein revered Boltzmann in the sense for the kinetic theory, statistical mechanics, and other things. Ludwig Boltzmann's student was Paul Ehrenfest. And Paul Ehrenfest was a very well-known physicist. He also, you can see that, well, the whole idea is a nice idea, though it may be wrong, okay. But what he said was, Ehrenfest told these fellows, Stern and Gerlach, you both are not very well known in physics as a scientist. You have no reputation. Therefore, if you say something wrong, you have nothing much to lose. Okay? Your people will not say, such a great man saying such stupid things, the reputation is lost. So, Paul Ehrenfest told them, publish your idea. Okay? You have nothing much to lose because you guys are not very well known as a physicist anyway. Okay? You'll give a story about that. Again.
originally published in 1921 and 22 by Stern first, the experimental setup, and by Gerlach and Stern, the actual experiment and their findings in 3 papers in a series in 1922. So 1921 and 1922 is when this work saw the light of day. 1925, Goudsmit enters the picture. He had worked in Paschen's lab and tried to understand the Zeeman effect in the hydrogen atom spectrum and the anomalous Zeeman effect. And he found that the Zeeman effect was easy enough to understand in terms of the orbital angular momentum, but unless by 1925 he came to the conclusion with his colleague Uhlenbeck that unless they postulated a half-odd integer strange quantum number, intrinsic angular momentum, which is a half-odd integer, unless they postulated that.
Yeah, the term anomalous Zeeman effect came simply because this changes that they saw could not be explained in the hydrogen spectrum using the orbital angular quantum number of the hydrogen electron. You know, all of you know about the s orbital, the p orbital, and the d orbital. So these orbitals have what are called the orbital angular momentum quantum number. The s is 0, the p is 1, and the d is 2, and the f is 3. In chemistry, we do not go beyond the f, because the farthest, the heaviest of the atoms has only 5f orbitals and 4f orbitals, not more than that. We don't have g orbitals in chemistry. Therefore, L equal to 4 is not needed. So, they studied the hydrogen atom spectrum using orbital angular momentum idea. They could explain some part of it. Goodsmith. That's the normal Zeeman effect. The thing that they could not explain, they called as anomalous. What is anomalous? Anomaly is something, in English it means something that is not regular, something that is out of the ordinary. We don't understand it. And that non-understanding of the Zeeman effect, they called it as the anomalous Zeeman effect. And the anomalous Zeeman effect, they could calculate and explain if they introduced an intrinsic quantity called another spin quantum number for the electron, and they introduced this arbitrarily. You remember Niels Bohr also did the same thing. Niels Bohr simply said that the electron will go around only those orbits in which the angular momentum of the electron will be integral multiples of h by 2 pi. Why should it be true? Nobody knew. But it worked. And Niels Bohr came up with a beautiful explanation for all the hydrogen atoms, and he reduced the Rydberg formula, the Rydberg constant that was there arbitrarily as a number. He gave an exact theoretical expression for the Rydberg constant, and it matched. That's how Niels Bohr became successful. And then he later understood there is a fundamental problem with the mechanics of the atoms. The Newton's laws don't work. There is a quantum problem and so on. Same thing happened here. So if you read it carefully, for formal reasons here, Sommerfeld's hydrogen atom, for formal reasons, they had done that. He had investigated all those things. He obtained a new interpretation of the hydrogen atom, the new term scheme. And the curious thing is that I is Goudsmit, because I knew all these intensity rules and so forth had already guessed the correct formula. I knew which formula one had to take. One took the classical expression, instead of integral quantum numbers, one put in half integral quantum numbers and did a few things. It was like magic, but it was all working all right. Then the forbidden line, which Paschen had seen, was not forbidden, but a real spectral line. It had to be explained, and it was present. So Goudsmit had already guessed something called a spin at that time. He gave an arbitrary name and a number for that. Now, let's go through the lecture.
In the anomalous Zeeman effect. So Goudsmit says one of the first results that came out was a new interpretation of the spectrum of the hydrogen atom, anomalous Zeeman effect. We had Sommerfeld's hydrogen spectrum, and for formal reasons, and because I had investigated all those things, says Goudsmit, we obtained a new interpretation of the hydrogen spectrum, the new term scheme. And the curious thing is that because I knew all these intensity rules and so forth from my visit to Paschen's lab, I had already guessed the correct formulae. That was my contribution. I knew which formulae one had to take. One took the classical expressions, and instead of integer quantum numbers, one put in half integer quantum numbers, did a few other things. It was like magic, but it precisely fitted. And what I found so delightful, if you believed it, was then the so-called forbidden transitions due to the anomalous Zeeman effect, which Paschen had seen, was not forbidden at all.
It's not forbidden.
That was a real spectral line which should be present. And that was, of course, a matter of source of great delight. Then when they wanted to publish this work, Ehrenfest apparently told Goudsmit.
My remark about this statement is not for Stern and Gerlach, but for these two, Goudsmit and Uhlenbeck. They were the first to discover experimentally the spin.
Well, that's a nice idea, though it may be wrong, but you don't have a reputation, do you? So you have nothing to lose.
Nothing to lose, publish.
So they went ahead and published it. Now the strange thing, ladies and gentlemen, is this bunch of publications was fully 3+ years after the Stern and Gerlach-Stern paper.
Stern-Gerlach experiment was 1922.
And these two bunches of papers were not connected in the community for another couple of years. In fact, as we understood after 1927, when R.G.J. Fraser seems to have pointed it out, the Stern-Gerlach experiments actually demonstrates electron spin. It is space quantization, but it is not the space quantization of a p state with a magical disappearance of the ML is equal to 0 component. It's nothing like that. And it is a spin half, and you get
SGE means Stern-Gerlach effect. That's what SGE means. So now you can see Fraser publishing something on that. Ronald Fraser did something, and then you can see that the splitting of the Stern-Gerlach is not due to the nuclei, not due to the silver nucleus, but due to the electron. And therefore only 2 beams were seen for the electron. That's what is the whole, that was the hidden story until all of, see how many times experimentalists make mistakes. How many times theoreticians don't think good experiments can be done, or experiments that you want to do is not very good, discouraging people. See, this is what is all about science. The whole spirit of what you are here is to understand that you make mistakes, but you recognize when you make mistakes and move immediately on instead of covering it up. Don't cover it up. Accept that that was a mistake, move to the next one. And here, Max Born made a mistake that nothing interesting will come out. Ehrenfest told these people that these are all very famous theoreticians. Oh, you can publish it, who cares for this experiment and so on, okay. And then Stern and Gerlach saw space quantization, but they misinterpreted it. They misinterpreted it as due to the silver atom's p state. After this 1925 paper, Ronald Fraser goes to re-explain the whole thing. So you make mistakes all the time, but you are smart and therefore you correct. Yeah.
Sir, could you explain the difference between mu z and mu b?
Sorry?
Mu z and mu b. What our
Mu z.
and mu?
Yeah. Mu is in the direction of the z now. B is the magnetic field in that direction. But there is a gradient magnetic field. Therefore, the magnetic field is not the same at all points of z. That's why it says dou mu by dou z. Okay. So if this is the direction of z, magnetic field here is different. If the a collimated beam has a certain width, isn't it? Therefore, there are atoms at the top, there are atoms in the middle, there are atoms at this. Each one faces a different gradient, different force. Each one faces a force. And therefore, each one is deflected differently. So, what you would expect, if atoms are in all these directions, all these places, each one will be deflected in some way or the other. And therefore, when they are deflected and you have a screen to measure, you will see that the whole thing will appear on the line. Okay? Now, that did not happen. You saw the picture. What happened was the line did not come in. What Stern and Gerlach thought was this is due to angular momentum 1, not due to angular momentum half. Therefore, they should have seen one beam which is undeflected. They did not see the beam. Therefore, they thought it was unobservable. Mistake number one. Mistake number one. Second, they thought that this was due to silver atom's own spinning or angular momentum, p state angular momentum. But the p state of the silver atom is that of the electron. Therefore, it is the electron spin angular momentum which they did not calculate. They assumed it as the orbital angular momentum p which gets deflected. It was not orbital angular momentum p. Orbital angular momentum p, if it is deflected, you should see three lines, 1, 0, minus 1. So they said it's plus mu b, this is 0 mu b not seen and minus mu b seen. Okay? They didn't realize that neither of their interpretation nor the pessimism of the theoreticians was correct. Goudsmit published a spin for the electron as an intrinsic property, and he explained the anomalous Zeeman effect with that spin a half proposal. So now you see, somebody has done something, they have introduced a spin a half. Somebody has done another experiment in which they have misinterpreted it, and then there is a whole lot of theoreticians who are saying this is not very useful, don't worry about it. And so another person thinks about all these things and say, no, there must be some connection between all these things. Read all the papers again. Angular momentum is the spin angular momentum is the one that leads to the magnetic moment property through a nuclear property called the gyromagnetic ratio. The gyromagnetic ratio is the EH bar by 2 mc. Okay? Gamma. This is a fundamental property associated with every charged particle going through an orbital motion. Gyro is what? Rotating. Magnetic ratio. So if the rotating thing has a magnetic moment, it's a rotating magnet, will always have something called a gyromagnetic ratio. And in the case of electron, it is related to the mass of the electron, the charge of the electron, the velocity is the speed of light, and the fundamental constant h by 2 pi. This can be calculated. It was predicted as a property, and therefore physicists have started measuring all these things afterwards. Okay? So magnetic moment is due to the fact that the electron has an angular momentum, and the magnetic moment of the electron mu is gamma j. So if the j is not there, you will not see a magnetic moment for the electron. Okay? So this is well known. This was known at that point of time. So I hope I answered your question. This is a property of the nucleus or the electron. Okay? Now, if you look at the electron, the mass of the electron is very small, right? Compared to that of the proton, it is 2000 times less. Therefore, the gamma for the electron is much bigger, 2000 times bigger than that of the proton. Therefore, when you use proton measurements and you study the magnetic resonance due to protons, you do them in the radio frequency field. But the gamma for the electron is 1,000 times more. Therefore, you see them at the microwave, which is 1,000 times more frequency than the radio waves. So the electron magnetic resonance, electron spin resonance happens in the microwave region, whereas the nuclear magnetic resonance happens in the radio frequency region, which is 100 megahertz. Microwave is 1 to 100 gigahertz, already a factor of 1,000. Okay, that's because of this number. The gamma for the electron is the largest among all the nuclear particles. All nuclei, protons, deuterium, then helium. There are 92 elements that you know are stable elements. Most of them are stable. Some of them have the special property that they have an even number of protons and even number of neutrons. But that's a one stable configuration. They have isotopes where the number will immediately change. The neutron number will change. Therefore, all nuclei have spin. All nuclei. There's no nucleus isotope, which is nucleus which does not have an isotope with a spin. So spin is a very important property. But this whole experiment is about the prediction of this in the history. No, the magnetic quantum number is the quantization number. Just like when you say the energy of the hydrogen atom is given by the principal quantum number 1 by n square. How did you get that n? Because the energy is quantized. Therefore, you are able to express this in terms of either integers or half integers. It's not arbitrary number. The same thing happens with the magnetization angular momentum, that when it is quantized, you will calculate the magnetic moment to be half h bar mu. Mu will be half h bar, and for the negative it will be minus a half h bar. Therefore, this number, half and minus half, become the quantum numbers for the energy. Yeah, some nuclei will be in the plus a half state, some nuclei will be in the minus a half state, and for protons and the electrons, the quantum number which decides the number of states is 1/2. And therefore, the number of states that you have is 2 into that 1/2 plus 1. 2 states. If the quantum number of the nucleus is 1, for example, deuterium, in the magnetic field, deuterium will have 3 orientations. One which is pointing towards the magnetic field, one which is neutral to the magnetic field, perpendicular, and one which is pointing in the negative direction. Therefore, it has 3 states called 1, 0, and minus 1, mu b. The quantum number is 1 because the spin quantum number associated with the proton is 1. It leads to 3 possible energy states. The spin quantum number of iodine nucleus, 127 isotope, is 5/2. It has 6 orientations in a magnetic field. 6 orientations are 5/2, 3/2, 1/2, minus 1/2, minus 3/2, minus 5/2. You remember LM in hydrogen atom? Where did that M come from? The M takes all the values of plus L to minus L with an integer step 1, isn't it? Same mathematics is applicable here. That's also angular momentum algebra. This is also angular momentum algebra. Therefore, the mathematics of angular momentum is the same. So the quantum numbers come because the eigenvalues or the measured values are fixed numbers. They are not anything in between. So those fixed numbers are variations, and the base number is 1 or half or 3/2 or 5/2. Now you take the square of the magnetic moment. So square of the magnetic moment, if you do for a spin a half, it will be 3/4. It will not be 1/2. It will be 1/2 into, you remember I into I plus 1 rule. You would have studied in inorganic chemistry. Magnetic moment. In crystal field theory, you would have studied the number of nuclei, number of electrons. If they are 4 electrons are there, the total magnetic moment is 2, and therefore 2 into 3, 6. You have done that, root 6. You say that. That's a square of the magnetic moment. If you take any angular momentum square, the eigenvalue, the measured value that you will get is that quantum number into I plus 1. You won't get Z. That's the reason why if you say that my angular momentum is this, okay, if this is the magnitude, okay, it should be I square, but it's not I square. It's I into I plus 1. What is I? I is the projection of this. This is I. This height is I. And this will be I minus 1. I minus 1. All the way. Minus I. So the orientation of the magnetic moment in an external field is at an angle such that the magnitude of the magnetic moment is not the same as the Z component. The magnet will never align like this or like this. Only if it does, the Z component is the same as the magnitude. The Z component is never the same as the magnitude. The maximum value is I, the magnitude is I into I plus 1. This is never 1. This is cos theta. Okay? The angle theta. For a spin 1/2, what is that number? For a spin 1/2, if I is 1/2, what is that number? 1 by? Okay, 1 by root 3. So, if I have to write this as an equation, can I write this as 3 cos square theta minus 1 is 0? Zero. This theta is called the magic angle. Magic angle. Magic. In physics. Okay. Actually, if you have a spin 1/2 in a solid, which is oriented like this, and if you take the magnetic field and you put a probe which is at an angle theta, the theta value is 54.7 degrees. 54 degrees 7 minutes, okay? So if you put a sample tube at this 54.7 and you rotate the sample tube, the signal, some of the magnetic resonance signal disappears because you are creating this condition in your experiment. You are putting the 3 cos square theta minus 1 to be 0. Therefore, some dipole magnetic moments cannot be observed, first order. So this is a real number. It's not something that you imagine. Experimentally, you can see that. So the orientation of the magnetic field means, quantization of the angular momentum means that the angular momentum can never point exactly in one direction, which means the Z component is one value, the X component is 0, the Y component is 0. You cannot have that. You cannot simultaneously specify all the 3 Cartesian components of a quantum magnet. That's because of this reason. Therefore, you say the magnet, if it is orienting this way, if it is static, you can still take a projection and say this is X, this is Y. It's not static. It is actually rotating. It's called the precession. The gyro effect comes there. The spin is not static in a magnetic field. The spin is precessing about the magnetic field such that the XY components average out to 0. You do not know the exact value. The average value will be 0 because some spins will be in this direction, some spins will be in this direction, some will be in this direction, equal number will be in this direction, they all average out to 0. Therefore, magnetic experiments tell you only 2 quantities can be measured simultaneously. The magnitude of the quantum, the magnet, and one of the components, which we call as the Z component. Okay? Fundamental.
And they have the Z component of plus minus mu b, the Bohr magneton, because the G factor is 2. The spin quantum number is half, but the G factor is 2. And so that was what was happening in the Stern-Gerlach experiment. So the puzzle remains that although it was all published by Stern and Gerlach in 1921 and 22, and then Gauss-Schmidt's hypothesis of spin half with Uhlenbeck in 1925 to understand the hydrogen spectrum and the anomalous Zeeman effect, nevertheless, nobody connected these 2 kinds of work. until Fraser came along and said, yeah, this is the same thing. That Stern-Gerlach effect is really the spin. 1927 was when he noted it. So if you look at a schematic diagram of what is happening, the oven producing the beam of silver atoms is here, then it goes through this magnetic field. You see one pole is really pointed and the other one is kind of scooped out, and therefore you have a huge gradient in this direction, the vertical direction, which the coordinate system is Z.
You see that?
Here we have shown the axis of...
You see the experiment? This is the magnetic field. South pole is reverted and the north pole is pointing. Therefore, you see in the Z direction, because of this varying gradient, in the Z direction, the magnetic field is not the same. It's one value here, it's another value here. Here the poles are far apart, here the poles are closer, Therefore, you see that there is a gradient in the Z direction. That the field is not the same in the Z. That's the reason why that gradient deflects the magnet, and all of the time, the final result, I don't want to play it any further, the rest of it is more mathematical than what it is. All of this is a spin down and a spin up. They calculated it correctly as half h bar and a minus a half h bar. Okay, the magnetic moments. And then Fraser reinterpreted this experiment as due to electron spin, not due to nuclear spin, not due to the silver atom. It is due to the electron in the silver atom, which has two orientations, and these two orientations deflect the silver atom, the p state or whatever it is, into two states. And as a result, you have two angular momentum components, a plus a half h bar and a minus a half h bar. What it means is that, last one, what it means is that if you think about the Z direction and you say if this is plus a half h bar and if this is minus a half h bar, this is a 0, okay, then please remember the magnetic moment is root 3 by 2 h bar. The magnitude of the magnetic moment is root 3 by 2, isn't it? I into I plus 1, square root h bar, okay. I is a half, this is 3 by, this is what? Half plus 1 is 3 by 2, square root, so you get root 3 by 2. Therefore, the vector is of length root 3 by 2 h bar, or it has in this direction a length of minus root 3 by 2 h bar. These are the only two orientations which are possible. And now you can see theta. Therefore, the vector is such that it is actually precessing. It's actually precessing in the direction. The spin a half is precessing in the upward direction like this. The spin a half in the minus direction will be precessing in the opposite direction. Therefore, you can't get an x component or a y component. Average will be 0, but the z component is always fixed because it is precessing with this as the axial. Therefore, the z has a constant value. Z can be measured, I square can be measured, but Ix cannot be measured, Iy cannot be measured. And these later became the most famous Pauli commutation rules in angular momentum. And then the whole theory of angular momentum is fundamentally important for spectroscopy, for magnetic resonance, for electron paramagnetic resonance, magnetism in materials, solid state, transistors, lasers, photon. Two polarizations corresponding to plus a half and the minus a half algebraic states. Photon polarizations are elliptic, two polarizations are possible, and those two are mapped to this. And finally, the quantum computer, which is also a qubit computer. We are very rarely coming into a Q-trit computer, but Q-trit will happen soon. It's a trit state is a 1, 0, minus 1 state. The bit state is half and the minus a half state. Okay, so experiments are happening, and your generation will determine where to take this forward. Okay, now it's time for your lunch. Okay, any other questions you have? Let me stop here because the rest of it is more descriptive, but it's very important for you to recognize the most fundamental experiment was fully flawed. All mistakes were made in that one experiment between 7 years. Somebody said the experiment will not work. Somebody said, I will measure this and I will make the experiment happen. And then he made the experiment happen, but he interpreted the results incorrectly. And the third person came and said much later, hydrogen atom, I have found out the half quantum number. And then finally the fourth person said, these two are one and the same, connect them. Yeah.
Sir, does the gradient of magnetic field in this have to be constant?
Gradient will not be, yeah, gradient will be constant because you see, the values of the magnetic field will be the same. Therefore, the gradient dou mu by dou z. You are saying whether there is further to that, some sort of a gradient of a gradient. Okay, I don't remember. I don't know. I think we can ask Bala about this. I think the gradient is a constant, if I remember. Dou mu by dou z is one value. See, the gradient is the force. The force is a constant. The force leads to acceleration. If the force is constant, the acceleration will continuously happen, right? Acceleration will be there, which means the velocity will be continuously changing. Acceleration is a constant. Yes, I agree with you. But then the velocity will be changing. Something like that you have to think about in the mu. I think the dou mu by dou z is a constant value. It's not an odd varying field. Yeah.
So, could you explain the cone again? Where exactly that comes from and
No,
what
no.
that
Why
means?
it is
Why the cone? Yeah.
not spiraling? Why it is precessing? Okay. No, the idea is that again we cannot measure the x and y magnetic moment. If the spins are static, then they have an x component and y component that can also be experimentally measured, isn't it? In a plane perpendicular to that, you can have a coil and see what is this magnetic moment, what is the corresponding magnetic moment, and then you can measure. You are not able to see it. And also, at thermal equilibrium, the spin preserves only the z component. Therefore, if the x and y component on the average has to be 0, you do not know whether it is orienting this way or whether it is orienting this way or whether it is orienting this way, but its quantization is with respect to this axis. Therefore, with respect to that axis, the spin can be anywhere, isn't it? Can be here, can be here, can be here, it can be there, can be there, and you have how many spins? Therefore, we say that the spin is not static. All orientations are possible, which means that the spin is precessing. It's not like your spin top. No, you can't have that picture. This is our visualization of saying that the orientation is not fixed to one direction, but all what is called axially symmetric. See, if this is the axis, it is axially symmetric about that, all orientation. That's why we call this as a precession. Okay. And this precession has a name. It's called the Larmor precession. Joseph Larmor was the one who first described this for a classical magnet. So this is called the Larmor precession. Okay. So